Now that we've developed some basic tools for studying representations, we shift focus to representations on function spaces. To motivate, let's consider our problem of full reducibility. So recall we had G a finite group. Pi v is a unitary representation of G. So here we have V a finite dimensional vector space over the complex numbers. And our result is V can be written as an orthogonal direct sum, W1 through WK, where the WI's are irreducible subrepresentations of V. Now, so I'm going to answer questions here. First, what kind of irreducibles can arise? So we want to be able to classify the irreducible representations of G up to equivalence. Then, once we have those, we want to know what are the projection operators that carry us from V to these subspaces. Now, we're only going to get a partial answer to that. To get these answers, we're going to have to study functions on the group. So that's going to involve analysis on our finite group G. And that's a subject that's interesting in its own right. Now, where do we begin? If I have a group action on some set X, we're able to transfer that action to the space of functions on X. Okay, so we have something like this. So, for example, we have a representation pi v. Okay, here we're going to have a group action on a vector space by linear transformations. Then I could transfer this group action to the dual space. So recall the dual space is the vector space of linear functionals on V. A linear functional is just a linear transformation from V to the complex numbers. So here we're just going to have X equal to V. Our action, we've seen before, is given as follows. So the way I transfer the group action is by pushing it to the inside of the function with an inverse. Now, what's nice about this, in general, if I start off with any X, okay, it need not be a vector space, it just need a group action, we automatically get a vector space by considering the functions on X. So this space is always going to be a vector space. Now, working with functions as vectors takes some practice. What we need to know, we could add two functions to get a new function, and we can scalar multiply. Once we check the other axioms, we'll have that our function space is a vector space. Now, with that vector space, we take the group action from the previous board to get a representation. So, we have the group action on functions from the previous board. We just push in as an inverse. Then we have to show that this is linear and that we have the group action property. So linear straightforward, and then we've seen the group action property when we've done this for the dual space. For a concrete example, okay, let's let X be equal to 1, 2, 3. I'll let our group be S3. We'll have the permutation action on 1, 2, 3. So the usual action. Now the space of functions on X, it's going to be three-dimensional. Okay, we'll have a basis, okay, F1, F2, and F3. Okay, so for instance, F1 sends 1 to 1, 2 and 3 to 0, and the others do likewise. Now, we have an inner product. Okay, so this is the usual inner product. Here, we only have finitely many points in our domain, but that's fine. Okay, and with this inner product, we'll have that our basis is an orthonormal basis. We have our group action to give us the representation. Then, with all of this data, we'll have that L, okay, functions on X, is going to be a unitary representation of S3. To check invariance, we apply the left action to F and H, take the inner product. So, we expand that out, we apply our left actions, then we do a change of variables. So we'll let X be equal to sigma Y, and then we're going to sum over Y instead. Now, that's going to give us the inner product of F and H. Okay, so the Y is just a dummy variable. So we see that we have invariance, and thus our representation's unitary. Now, to be sure, let's apply a specific group element to a specific function. So the group element that I'll use, okay, well, the cycle 1, 2, 3 in S3. Our function is going to carry 1 to 1, 2 to 0, 3 to -1. Okay, the point here is I just want our function taking distinct values so we can see where things go. Now, in our basis, this is just f1 minus f3. We have our definition of the group action. So what are we going to do? I want to consider all candidates for x. So it's 1, 2, and 3. We're going to apply sigma inverse. So if we have 1, 2, 3, the inverse is going to be 1, 3, 2. So 1 goes to 3, 2 goes to 1, 3 goes to 2. Now we're going to take this and stick it into f. So I'll have that 3 goes to minus 1, 1 goes to 1, 2 goes to 0. Then our function for left action is sigma on f. It's going to be 1 goes to minus 1, 2 goes to 1, 3 goes to 0. So in terms of our basis, we'll have minus f1 plus f2. A few other things to check for our representation. Okay, if I wanted to find invariant subspaces that are irreducible. First, we have the trivial representation represented by constant functions. Okay, so no matter how we apply our group element, when we have a constant function, the values always come out the same at each point. So the action there will be trivial, okay, and this is going to be spanned by, okay, complex numbers, span of f1 plus f2 plus f3. Since we have unitary, I would want to look at space that's orthogonal to our constant functions. Those would be the ones that have some of their coefficients equal to 0. So we're going to get a two-dimensional irreducible in here, spanned by f1 minus f2 and f2 minus f3. So looks a lot like our permutation representation from before. Now, other things to check. Okay, we'll have that these are irreducible, and we'll have that these are orthogonal with respect to our inner product, as expected. To motivate what comes next, we recall Fourier Series and Fourier Analysis. If these aren't familiar, then our approach is going to give some motivation for Fourier Series when you do learn them. So the formulas won't be so mysterious. Now, here, we're in the special case where the group acts on itself. And then we have options. So the group can act on itself either on the left, on the right, by conjugation, or we can have G cross G acting on the left and the right at the same time. For a simple example, let's consider G equal to the two-element group represented as plus or minus 1 under multiplication. Then, okay, for our vector space, we have functions from plus minus 1 of the complex numbers. So this space is two-dimensional. Okay, we have basis given by f sub 1, carrying 1 to 1, minus 1 to 0. Then f sub minus 1. Okay, 1 goes to 0, minus 1 goes to 1. For our group action, okay, so G is acting on itself. And that'll just be, we're going to multiply by 1 when we act by 1. We multiply by minus 1 when we act by minus 1. Now, with this, we can make a representation out of our function space. Then let's consider different types of functions. So let's consider a function which acts according to a trivial representation. So in this case, what happens? Well, if we let G be equal to 1, nothing happens. We just get functions equal to itself. If we consider what happens with G equal to minus 1, then that says f of x equals f of minus x, and we're just considering even functions. So the even functions are going to have trivial action. On the other hand, if we consider the sign representation, okay, so this is going to be the one where we multiply by G itself, what happens here? Well, again, when G is equal to 1, we get nothing special. But if I let G be equal to minus 1, then we're going to have odd functions. Now note, every function, okay, on our two-point space can be written as a sum of an odd and an even function, so it's going to cover everything. Okay, we know that because our space is two-dimensional. So if we break things down in terms of representations, I'm going to have another basis. Okay, so trivial is going to be f1 plus f2, the evens. The odds are going to be spanned by f1 minus f2. Okay, put them together, we get everything. Now, some things to note. Okay, we could choose our inner product so that here we have an orthonormal basis. Then I can apply Fourier's trick, Parseval's identity to functions. We also note that these functions here are going to correspond to the characters of our two-element group. So this is going to be a general phenomenon for abelian groups. For a familiar example, we consider Fourier series. Now, if this example is not familiar, then the rest of the course is going to be motivation. To begin, we consider functions from the reals of the complex numbers that are periodic, period 2 pi. So we have f of x plus 2 pi is equal to f of x for all real x, or f just repeats every 2 pi. Now, familiar cases, we have cosine nx, sine of nx, where n is an integer. So these are just going to be waves that keep repeating. And we could take any linear combinations of these functions. Now, if I want a complex vector space, I'll take all functions in this form that are also continuous. Okay, we'll denote this space as follows. Because these functions are continuous, we can integrate over any finite interval. That lets us define a Hermitian inner product. So the inner product of functions f and h is given by 1 over 2 pi. You can take definite integral from 0 to 2 pi, f of x, h bar of x dx. Now, we should show that this is a Hermitian inner product, so I'll leave that to you, but we should note, because our functions are periodic of period 2 pi, okay, we don't need the whole real line, I just need the interval from 0 to 2 pi. That'll catch all the information we need for our functions. Then, because we have periodic of period 2 pi, we can replace the limits with any interval of length 2 pi. So I'd go from minus pi to pi, pi halves to 5 pi halves, whatever's convenient. Now, to continue, we would need an analysis class to make things precise. So here we just list the main results. Now, we'll take our inner product, we'll complete that space. So it's going to give us a space called L2 of S1, and more or less, it's going to be the space of all functions whose length squared with respect to the Hermitian inner product is defined, or a finite number. Now, for this space, we take all the functions of the form e to the inx, where n's an integer. We're going to get an orthonormal basis. So we can apply Fourier's trick and Parseval's identity. Now, Fourier's trick, what we do is, for c sub n, take the inner product of our function f with the nth basis vector. So that's going to be given explicitly by this formula. Now, what we've done, we're taking a function, we're going to assign it to a sequence of complex numbers. With this sequence, we could try to reassemble the function into what we call a Fourier series. So the idea is we're going to take each of these coefficients, match them with the vectors from the orthonormal basis. So it's going to give us a series as follows. Now, questions we need to ask. First, for what x is this series defined? Then once we have that, we have to ask how different is our Fourier series from the original function? Okay, these are questions for class and analysis. Now, once we have these, we also have Parseval's identity, which just says the length squared of our function is equal to the sum of the length squareds of our coefficients. We can recast the previous picture in terms of the representation theory of the circle group. So, if we have a function periodic with period 2 pi, we can identify that with a function on the circle, specifically the unit circle in the complex plane. Now, the way we make this identification, if we have any real number, I can exponentiate to get a point on the unit circle. If we take a point, add or subtract 2 pi, exponentiate, we get the same point on the unit circle. So this map descends to the quotient group. Now, pictorially, all we're doing, taking the segment from 0 to 2 pi, identifying the endpoints, and then we get our circle. Now, some things to note. First, we have an orthonormal basis in terms of exponential functions. So where did these come from? Well, it's going to turn out these exponential functions are precisely the continuous characters of the circle group. So if we're looking for one-dimensional representations of the circle group, they're all going to be in this form. It also turns out all irreducible representations of the circle group are in this form. Now, we could talk about Fourier analysis for real-valued functions. So then, instead of using the exponentials, we would use cosine and sine. And then we have to adjust our normalization a little bit. Now, the way we go from exponentials to cosine sine is through Euler's formula. So e to the I nx equals cosine nx plus I sine nx. Then there's a way to get the I to come out. Now, for more representation theory, okay, to get to our previous picture, what we want, I want a group action on the space, and then we want to push the group action to functions. So here, our group and our space are the circle. Okay, our action is just by multiplication. Then we'll use the left action. So we'll push our circle elements to the inside of the function with the inverse. So we have a minus sign. Now, if we consider the functions, okay, I'm going to distinguish between functions and characters or representations. So we're going to have sub-representations spanned by functions of this form. So you'll note if I apply, okay, our left action to one of these functions, okay, you work that out, what happens is it's going to pull out with the character with the opposite sign. So if I have a function given by raising e to the I theta to the nth power, with the left action, we're going to multiply by the character with minus n. Now, the story we want to tell for finite groups is close to the story for the circle group. First, we have the left action acting on our function space. It's going to be a unitary representation of our group. If we decompose this space into irreducibles, we'll see that each irreducible representation of our group occurs exactly once. Now, we could state that as is if our group's abelian. If it's not abelian, then when we say irreducible representation, it's going to be of the group cross itself. Now, if we want an orthonormal basis for the function space in terms of the representation theory, if our group's abelian, then we'll just use our characters, our one-dimensional representations as functions. If our group is non-abelian, then we'll use matrix coefficients for each irreducible representation. Okay, and the matrix coefficient functions are close to the characters. We'll also look at some advanced features from Fourier analysis. So the first part is going to be the Fourier Transform. Okay, so we had Fourier's trick, which took any function that was nice enough, we assigned it to a sequence of complex numbers. Now, there's more to the story here. One thing we'll say is that this function, okay, we consider this as a linear transformation between vector spaces. In our case, it'll be invertible, okay, and then the inverse is just going to be take those coefficients and reassemble your vectors using the orthonormal basis. We'll also have convolution. So I won't define this here. What convolution is going to give us is the projection operators from our function space to the irreducible sub-representations. So it's just going to be given by taking convolution with your character of interest. And we'll say more about that later.